Well, again, folks, I'm in a different location today just to sort of test the audio capabilities of this room. I'm a little afraid to turn off my projector here because it took me a while to set it up, so it's going to be running, and hopefully that fan is not too annoying. Anyhow, today, let me turn off the light. This video is specifically for section 3.5. Which is about transformations. The packet that I have for you consists of these pages. I'm going to have to keep turning the light on and off. And just a quick overview of this. All right, something to print out. This is the collection of transformations. I regret that I put this in gray, but it was more or less just to emphasize these positions in this sort of formula model here. We're going to get into it in a minute, but the gray allows me to sort of emphasize that there is a feature here that is important. All right. So do print this out if you're following along. All right. This is an older piece of paper. Again, I don't know what it is with this copy, but this should say Toolkit Parent Functions. Anyhow, you have this from a previous packet, but I want to go back and sort of emphasize some details here because it'll be useful if you have to sort of figure what the transformation model would look like, unique to some type of equation. There is some graph paper. And there's two things. This is something that I swiped from your actual textbook. It has a couple of typos down here, so I wrote my own to sort of reiterate the information. And I'll go through this in detail when we get there. And then there are some diagrams that I purposely left blank, just so you can annotate if you're following along. I want to sort of improve this a little bit as well. And then lastly, there's this diagram which has to do with symmetry. I'll give you an example of the symmetry of each of these scenarios. All right, so if you're following along, I do please print this, especially because it will help you do your homework. And we'll get started. Way, and I'm gonna hit the lights again. I'm sure if I can tell already, so I'll move my chair out of the way here. In fact, let me put my book in a different place. Need a podium, that's what I need. Furniture here real quick. Oh, look at that. Anticipated. It's a little difficult to see in the dark, but do the best I can. All right. Let's start with this diagram, types of transformations. Here. Right, it's a little far away. Let me fix this. We'll discuss this. In fact, I'm going to have to move this over slightly. I might get to be a little bit bigger. All right. That's a little out of the frame. So what I'll do is I'll slide it over when the time is relevant. All right. This is an overview of different transformation types. Again, I put this in gray just to sort of put these highlighted features that you see here. Just hold on to. This is especially something that will be useful to you, right? Just to pay attention to the letters A, B, H, and K, and plus and minus, and this minus that's there, all right? Any type of algebraic function, right, can basically be adapted, right, to for lack of a better word, superimposed upon this, or vice versa, so that you see what features are there and which features are missing, right? If there is a feature, that is to say an actual number that's sitting up in front of a parentheses, all right, it has a certain job, all right? If it has, you see numbers that are specifically in either one of these locations inside the function, inside the parentheses in this case, all right, they have a different job, right? That's what you have to sort of imagine transformations to be like. They're things that you can do to an algebraic equation, right? Function, I should say. There are, in general, there's two types, right? There's what are regarded as rigid transformations, right? And then non-rigid transformations, right? More or less, right, rigid transformations involve moving the picture around, all right? Non-rigid are not moving them so much as stretching them in some way, morphing them, you might say, all right? Of the rigid type, there's two sort of categories we consider the sort of shifting and the reflecting, right? You can think of it in just a different phrase here. Shifting is sliding things around either vertically or horizontally. Reflections are flipping something over an axis so that it may look upside down or backwards in some cases. Depending upon the type of algebraic function, you may not even notice that something has happened, unfortunately, because of the symmetry of them. Right? Anyhow, this non-rigid type, there are stretches, all right, which is usually, you can think of pulling in a certain orientation, right? Pulling horizontally, pulling vertically on your graph, right? So that it's morphed, it distorts the picture somehow, right? Compressions are just the opposite of that. You can kind of think of them in the context of squashing something, pushing rather than pulling, right? Pulling is going outward, pushing is more or less inward. That's what stretches and compressions are, right? Anyhow, if there is a number, all right, that is sitting in these positions in your algebraic function, all right, they'll have that job to do, right? I made this sort of a rainbow-colored chromatic here, all right, to make it, you know, as distinct as I possibly could. When it comes to the non-rigid type, the vertical stretches and horizontal stretches, all right, there are some, they're a little bit trickier because you have to consider what the magnitude of the number is, all right, what the effect is going to be, right, vertically or, you know, horizontally. Anyhow, let me come back to this in a minute. I want to reiterate some information from maybe last class, when the subject of different function types came up. Not this one, I'm sorry. I have to dig for it, I'm sorry. This overview that you have from here. Take a look at this for a moment. This is not the limit of what we have, all right, in terms of algebraic functions. But these are the ones that are relevant for right now. They're the algebraic type. Right? There are the transcendental functions coming towards the end of the semester, the non-algebraic type. And it would be good, strategically, in the long run, to commit these basic shapes to memory, right? The gist of it is that if you can just zero in on the X, it's a bit small here, but if you have the photocopy handy, this will be easy for you to read. Things that are of degree 1, if you zero in on the exponent, right, of the input variable, in this case, the independent variable is this, right, X, right? They decide ultimately the shape, for lack of a better phrase, of this picture, of this drawing, right? If you just tinker with that, all right? Turn you a math god for a second, and you up the ante one number from, say, degree 1 to degree 2, you get this the parabola shape, all right? These are what make these functions unique, right? Tinkering with that little mechanism, all right? what we're going to get into today, transformations, is taking these types of drawings, all right, and distorting them somehow, either stretching them or squashing them, all right, or shifting them around or reflecting them, right? Those are transformations. And that really just entails maintaining, if you want to just continue with something that is degree 1 or degree 2, say for example, just putting a number here, right? Or putting a number behind it, or putting a number, just encapsulating it in parentheses, right? It has these effects, these transformation effects on the pictures, right? Again, degree 3 would be down here, the staying alive sort of pose here. And then there are these other ones, which are good to know. You might look at the square root function here and go, well, that doesn't have an obvious degree, but eventually what you realize is that a square root is really just a degree of a fraction, right? As opposed to a regular ordinary whole number. Right? The cube root would be the same thing. X to the 1/3 as opposed to, right, reading it with the radical symbol, right? Then you have something down here, the reciprocal function, which is chapter 5, right? These are, this is a subcategory of a very specific type of a rational function. These are the type that have a negative integer as opposed to a positive integer. Right? We're going to go with the most easy one, would be -1. It ends up being 1 over x. And these are interesting, not to jump the gun, because they produce a graph like this, right? What I really want to emphasize right now is this. There are some good, aside from identifying the basic shapes, right, of say these 6, and then there's the absolute value, is the V-shaped one underneath. What you should try to commit to memory is that there are some important points that make up these straight lines and these curves, respectively. So, for example, if you have this piece of paper handy, right, what I would suggest is know these points. Because they show up not all of the time everywhere, but consistently. -1, 1, for example. 0, 0, the origin, 1, 1, right? You'll notice that they have the most basic incarnation of each of these functions, more or less those points in common. They're not the same drawing ultimately, but they would be good to know that they are comprised of those dots, literally, right? On this piece of paper, maybe if you have it printed, put a dot here at the origin, that would be 0, 0. Put a dot here at 1, 1, that would be here, this point here, all right? Put it in the case of a linear function here, the identity is the most basic type, -1, -1, right? To know 2 or 3 of these per graph will be handy when you get to having to say, make an educated guess as to what the transformation would look like, right? If you know a couple of points, you can perform basic arithmetic and more or less do these things by hand if you had to. Largely, you're going to be using your calculator, of course. There's no sin in that. It will certainly expedite things. But we'll do a couple of problems by hand, and you'll see how just knowing these points will make it easier for you to figure out what the distortion would look like, the transformation, all right? Following along here, all right? A parabola, that's just as simple as x squared, all right? Has that in common, 0, 0, all right? Similarly, 1, 1, and -1, +1 in this case, all right? 3 dots, good to know here, 3 dots, good to know here, all right? When you get to square root, I would say 2 is probably sufficient. The origin, 0, 0, and in this case, 1, 1. You could figure, though it would be technically off this graph a little bit, square root of 4 would be +2. But 2 is sufficient, right? Notice something. I don't want to jump the gun again, but this is more or less, it's similar to a parabola shape, in that it's not quite a U, it's not quite a V, it's sort of the bastard redheaded stepchild. And it's also crocked. As a technicality, all right, what would be the negative y values are excluded when you're talking about square root because it would cease to be considered a function by definition. All right, the official definition of a function is that there are no repeat x's. All right, so if you have the same x with two different y's, which would be the bottom half of this, right, it would cease to be considered a function. So even your calculator, were to draw this, will purposely exclude the bottom of that. All right, it has to, just to qualify for function status. Right? Anyhow, it's a similar looking shape to a parabola, just more or less sideways. All right. Now those 2 points. Here's the cubic yx3. Again, 0, 0, good to know. Right? 1, 1, and in this case, -1, -1. The staying alive sort of pose. All right, I mean as in Saturday Night Fever, right? Cubic, 0, 0, 1, 1, -1, -1. All right. Also good to know. It's more or less looks like this, sort of sideways and reflected. The reciprocal, the most basic type of rational function. Notice it doesn't have 0. This is one that does not incorporate 0, 0, the origin as any portion of the picture. Because this thing, when we get into chapter 5, has something special. All right, this has what I'll refer to as asymptotes. Right? It specifically has an asymptote that runs vertically through 0. All right, that is x equals 0. And a horizontal asymptote that runs through y equals 0. So horizontal and vertical asymptotes. All right. However, there are some points again that would be good to know. All right. If you analyze this, -1, -1, and +1, +1. All right. You can't memorize everything, but strategically, again, if you had to do anything by hand, or at least make an educated guess as to what the transformation would look like, to know a couple of points from each is handy. All right. That's why I mentioned it. There is another one that's out of the way of the projection, the absolute values, so maybe just scoop this up real quick. All right. This parent toolkit functions, 2 different names to refer to these in general, is what should have been on this piece of paper instead of that big square of ink. Anyhow, if you notice here, the absolute value, it's got a V shape to it. Again, origin 0, 0, good to know, 1, 1, in this case -1, +1. Right. That for right now would be practical to know. Okay? Let me get back to the transformations themselves and their effects. Right. I don't have on this computer, unfortunately, Texas Instruments, so I'm going to have to show you anything I can on this. All right, or else doodle by hand. Get this out of the way. All right. Now, here are the transformation effects. All right, let's say that you had, and you don't have to put it in function notation of f of x. You can just simply write y, right, in lieu of that, right? If you had no other effect going on, but something that is in the position of k here, that is an added number that is outside the function. I should actually mention that as well, right? One thing to sort of keep in mind, right? The vertical transformations, if you want to think of them as being the vertical effects, so the vertical controls, right? All the vertical controls are outside the function. This is going to fall, so I'm going to move it. There's this ever so slightly. Someone handled it when I shouldn't have. Oh, it's whooping. Anyhow, all the vertical transformations, all right, are outside the function. So what was regarded as inside and outside is basically a parentheses in the model. All right. So if you have the most basic transformation that is a vertical shift, there is a number that would sit outside of the actual function that you have. So the example that I have here is y equals the absolute value of x, right? And here is what you would see if you were tinkering with your calculator or you did it by hand, all right? What the vertical shift effect would be, all right, if you just put a number here, in the case the most simple number you can think of, right? +1, all right? What that is going to do is take the V shape and simply scoot it up the y-axis, right? Nothing too complicated, right? Let me show you with my own calculator here. All right. If you were getting your calculator to draw the pictures for you, as largely you will, all right, it's really just two buttons, all right? It's y equals in graph for all intents and purposes, right? If you want to get, say, something like the absolute value example that I have here, all right, then you can go through, there's probably more than one way to do it, but let me turn it on. My battery's getting weak, but we'll see. I can finagle this. Hit y equals, I have some stuff in here, so I'll clear it out. You get to this page here. The easiest way for me to remember is to hit the math button, scroll over to num, and you'll see the first function you have is ABS. This is absolute value. Choose that, and you see that you have the modulus lines. All right. Inside, you can put a variable. This button, x tau theta n, is automatically set to x, so you don't have to go hunting for it. Anyhow, this will draw, once you hit graph, the V shape. Bear in mind, it's going to be a little bit distorted because of the rectangular shape of this. All right, so it's not really mathematically square as it should be. This is just to accommodate us, I guess, our stereo-optic eyes. Anyhow, if you wanted to see those points, as I mentioned earlier, 0, 0, 1, 1, and so forth, all right, hit trace, all right, the cursor shows up, and around here you can just enter a value for x, and it will spit out, when you hit enter, the value for y, 1, 1, all right? Now, if we were to inspect, basically, again, this most basic transformation effect, the vertical shifting, again, outside of the absolute value, right? Because all vertical transformations are outside of the function, those controls, right? If you just park a number here, that's in the K position in the overall model here, all right, of 1 or some other number, right? You'll see the effect on this, and it should superimpose one drawing on the other. I'll go back to y equals, and just underneath this, do the same thing. Math. Let's see, scroll over here, absolute value. Put an x in there, and then on the outside of this, put +1. All right, and then hit graph. And then you see it draws another one with the minor alteration, the transformation, right? It's just the V shape up, right? Because it's a vertical slide, a vertical shift. And it's intuitive, all right? If you were to put a negative, it would be the V shape down, all right? Pretty easy, right? Let's take a look at this, all right? When it comes to the horizontal transformations, one thing that you have to be careful of is that they, all horizontal, transformations are inside the function. That means that they'll be in the parentheses, right, adjacent to the, if it's x is the input variable. Or in the case of absolute value, they'd be in the modulus lines, right, not outside, right? These are a little bit more of a pain in the neck as well because, I'm going to put it here, all right, the signs are counterintuitive. So when you see it written that there is a minus and then some number in that position, all right? Understand that the effect is exactly the opposite of that. It's counterintuitive, right? Meaning that when you think normally positive means you shift right along the x-axis, instead it is ironically shifting left, right? When you have positive, right? So if you see a positive, you're really going to shift ironically left instead, right? If you see a negative, all right, then you're going to shift right. It's counterintuitive. It's exactly the opposite of what you would expect. If you're wondering, well, geez, why is that? It's because basically something is partially factored, all right, if it's written in the parentheses. Right? I don't want to get into solving quadratic equations, but if you remember that stuff, one of the techniques for solving quadratic equations is factoring and then using something called the zero product rule. When you have factors, all right, from a quadratic equation, that's what they originate from, and the equation is set equals to 0, you can solve the two factors independently, right, using them set equal to 0, right? And what you end up with is something that is the opposite sign every single time. Right? Why? Because it's an equation and you start shifting things over and equals. Anyhow, without complicating it, just convince yourself. Horizontal shifting is counterintuitive, so the signs are going to be the opposite of what you would expect. Right? So here's what you would see in this case, x plus 1 inside the absolute value. All right? You take your calculator once again, all right, go back here, all right. I'm going to put absolute value in here again. I'm going to do this really quickly because it's easier looking at it. X, and then put, in my example, plus 1 here, plus 1, and then scoot outside of it. It's inside the function, because as all I mentioned, all horizontal controls are inside a function. All right, then you see how it affects it. All right, it moves it in the opposite direction of what it normally would be. All right, again, we think positive is right, all right, but instead positive is left when you're dealing with transformations, right, inside the function. They're counterintuitive. All right. Now, the next ones, the reflections, right? Reflections can be flipped over an x-axis or flipped over a y-axis. It's a little bit confusing, but when you flip over an x-axis, the horizontal axis, what you have is a vertical reflection, right? If this is the x-axis on the Cartesian coordinate plane, this is the x-axis. Anytime you have a drawing and then you flip it over that axis, it's vertical, right? If you perform a horizontal reflection, right, that's flipping over the y-axis alternatively. Okay? Takes some getting used to, naturally. All right? This, what I use here, these examples, of degree 2, x squared, and the cubic function are a more satisfying example to illustrate this type of reflection and this type of reflection respectively. So I'll do that again here. The batteries are low, this one here. I gotta clear out my old stuff in here, and then I'll show you. All right, back to y equals. All right. If you just want to get x squared and illustrate, all right, here's x. There is a button for squaring, of course, this one, so you don't have to use the caret. That's an alternative if you like. And then a digit. And here is how the graph would look. All right, the classic parabola shape, of course, right? Now, if you wanted to, again, vertically reflect it, right, that's a sign in this case, not the number per se, right, but the sign up in front of the value, the function. One thing you have to remember when it comes to something like y equals x squared, if you put a sign up in front, in this case I put a negative here, right, to illustrate, that is not affected by the square, all right, the operation that is squaring, all right, it would have to be encapsulated in a parentheses along with the letter and the degree written on the outside in order for that 2 to have any bearing on the sign as well, right? You know that when you square something, of course, it's an amped up turbocharged form of multiplication, which means it's the base thing times itself, right? So if it was a negative number times itself, it would be a negative number times a negative number. Anyhow, just putting this sign on the outside causes the vertical reflection transformation effect. And what you're going to see is simply the parabola upside down. So, back here again. Very carefully, I'm going to put parentheses just not to fudge it. Be careful, the Texas Instrument calculators are very nice, but when you are trying to put a coefficient sign, use this button down here, don't use minus, it doesn't understand that they're the same. All right, so put a minus here, all right? Now use your parentheses, all right? And then you can put x squared, all right? Close the parentheses just to be a good sport, all right? Negative is just out in front. It's a -1 technically, all right? But we're just considering it in terms of a sign effect. All right, here's the graph. You see that you have the same parabola shape upside down as effect. Okay, next one. Horizontal reflection. Again, the best example to illustrate something has actually occurred, I felt, was the cube root, all right? In this case, this is also controlled by signs, but it's a horizontal reflection, all right? And it's just a negative value that is written inside the function. So in the case of the cubic, cube root rather, since it's a horizontal and they're all inside the function, you'd have to have the negative actually written inside, underneath the radical, right, for it to have the horizontal effect. So I'm just going to put an X here, right, and you'll see what the graph looks like before and after. Clear, clear. All right. Cube root, if you want to get to it, there's, again, more than one way to do this, especially if you're fine with the menus up here. The math button serves me well, so you could see if you press math, option 4 is cube root. So you have that, and here's just the regular version of this, right? It's kind of the sideways version of the staying alive pose. And this is the graph, right? Kind of cool, a little slow. That's weird, I don't remember it looking like that. I'm writing it backwards, sorry. I think my because I put a square in it. Shame, shame. Sorry, I put this 2 here, it's superfluous. Delete that. Oh, you're so finicky. There it goes. So it doesn't like that. See the little box there? Sorry. There you go, calculator. You happy now? It's awful reading things backwards, but there you go. All right. There is the staying alive pose, kind of sideways, which is what cube roots produce, right? For lack of a better way of describing it. Anyhow, what you will see as a horizontal reflection, which means we're going to flip the whole graph over the y-axis, meaning like this orientation. All right. It'll be this shape backwards. It might look something like DNA if you want to get creative here. I gotta put it back, sorry. Here it is. I'm gonna look at it in the normal orientation first and then show it to you. All right. Here are the two as they would be entered here. And here's the graph. All right, there's the original one once again because I deleted it. And here's the other half of it. That's the reflection. Kind of cool, right? Looks like chromosomes. All right, moving on. When it comes to the non-rigid transformations, these are a little bit tricky, and to really get some kind of satisfaction for the effect, I chose these basic toolkit parent functions because they make it easier to see something has actually changed. All right, so we'll start with the vertical stretching. Right, if you took the same cube root, all right, which you know is a graph that basically looks like this. If there's a vertical stretch, what you're going to expect is the graph kind of pulled, all right, vertically up and pulled down, all right. How does one accomplish that? By parking a number now specifically out in front of the function, all right. So in this case, just putting a 2 here as opposed to say a 1, all right. It is understood, remember, that the coefficient of any variable is 1 if it's not written. So if you don't see a number there, assume it's positive 1. Right? Anyhow, this effect, for this to occur, that coefficient up in front of the cube root in this case, has to be something larger than 1, which is why I put A is greater than 1. Right? If you choose something smaller, right, in terms of the magnitude, what you get instead of a vertical stretch is that you get a vertical compression. That's the reason why I put this in blue and this in blue as well, right? Because they're both controlled by the same thing here, A. I'm sorry, it's outside of the frame, right? Let me smooth this over a little bit if I can. That's better. The number sitting in the A position, just the digit, right? A, right, controls vertical stretches and vertical compressions respectively. They are dependent upon the magnitude of the number. A number is either greater than 1, even if it's 1.1 or something infinitesimally tiny. That's just a smidgen bigger than 1. Or something that is, we're not considering negatives, something basically ping-ponging between 0 and 1, right? So like a half, right? You'll see that effect when we get there, right? A controls vertical pulling or pushing, right? I should say in this orientation because it's vertical, right? Pull, push, all right? Compress, same difference, right? So going back to this, I'm going to delete out the second one here, right? Here's our original cubic, all right? To illustrate this point, I am just going to replicate this for the second one to superimpose it and put a 2 in the front, and you'll see what the effect is. Here's a 2, 4, and then I put an X inside. So you see this, right? Vertical effect outside of the cubic, outside the function, all right? As all verticals are, all right? Here again, it's going to draw the original graph of a cube root. I shouldn't say cubic, it's a cube root. Cubic is just degree 3, all right? And now the effect, all right? It is pulling it upward and pulling it downward vertically. Kind of neat, right? What you would expect, and it may not be a little bit hard to see with too much on the screen here, is just opting for something between 0 and 1 is going to, ironically perhaps, make it compress. So there's a couple of ways you can do that. I'm going to do it nicely. Right? You could just put 0.5 for a half, but I like to put things in the style of a fraction if I can help it. Now that I have the opportunity, I'll tell you how to do it. All right. There's probably a menu option up here that can get to you a little bit faster, but the math button works very well. If you want to enter something in the style of a fraction, right, scroll over to num and go down to the bottom here. n/d is the fraction, right? And it's very intuitive. A number over a number. And so I'm going to put 1 and then 2 here, and this is still outside of the cube root. So I'll put that next to it now. 5. Delete. It's hard to see in the dark, I'm sorry. 4. X. There you go. And you have that. Coefficient of 1/2 or 0.5 would be sufficient again. And then you have that. All right, here's the graph. And you'll see that it gets squashed. All right, it's compressing. All right, it's the same basic idea, all right, but vertically compressed. All right, it's you might say pushing as opposed to pulling. All right, similar to the effects of vertical stretch and compression, that they're controlled by the same feature in your model. All right, B is the thing that controls horizontal compressions and stretches, respectively. All right, again, the best example to illustrate that effect, I felt, was the actual cubic function, degree 3. So let's do that. All right. Here, let's get that out of the way. To clean this later. Here's what the cubic normally looks like. Just for reference, it's the staying alive. I keep saying that because it's the easiest way for me to remember it, and I mean that pose basically from Saturday Night Fever, from dancing. Anyhow, that's the basic gist of it, right? If you have a horizontal stretch, it's going to basically pull it this way, right? So what you should expect is that you get something that looks a little bit more like this, right? All right, for a horizontal stretch. How do you induce or create that effect? Again, horizontal transformations are inside the function, so you would have to encapsulate the variable with the coefficient of a half, say, right, inside the parentheses, right? In this case, it's exactly the opposite of what you had before, which is for stretching vertically, you want a number greater than 1. For stretching horizontally, you'd want a number that, again, is between 0 and 1, right? The B value, right? The coefficient of x. So let me clear this out. And I'll delete this, I'm sorry. Here is our standard cubic. You'd have an x here. The easiest thing is to hit the caret symbol and then choose 3, and then hit graph. And you see that you have that nice shape. It's kind of also another way of saying it is that it's a parabola drooping on one side. Now here, if you were to, doesn't have to be that far away, be a good sport, put a parentheses in here, and then choose a half. You could do 1/2, but I just prefer to have it in the fraction style myself. So I'm going to do that. 1/2. Now put x, and then caret. Well, you know what I should do? I should actually put this outside. All right, sorry. Get rid of that. Parentheses. Now put the caret here. 3. There you go. Both of these things are inside the function, meaning they're both affected by the degree of 3. So the effect on the picture, as expected, is a horizontal pull, right? A horizontal stretch is the manner of speaking that you're more likely to read about, right? But stretching is pulling, all right, outwardly. Right? If, again, you're just tinkering with this value here, and you change the coefficient, right? It's still a horizontal effect, so it would still have to be inside the function, still encapsulated in parentheses, but you choose a number that's greater than 1. So the easiest thing is just to go with 2, say, right? You could expect, right, that horizontally compressing something is going to have this effect. Like that. A little bit more squashed. So here, one last time, is everything over 2x, close the parentheses, put a 2 there, dingy. 2, 3. Okay. 2 coefficient, both encapsulated in parentheses, they're both inside the function. And you hit graph, and you see a little squeezed version of the same graph there. All right, isn't that cool? All right. Now this is just everything all at once, mind you, and you do have some problems that you have maybe 2 to deal with at the same time. We're going to get into that. Worst case scenario 3, and even that's kind of rare. But what you take away from this is that just tinkering with something, right? This is the model, of course, right, where it's just kind of everything thrown in here. right, generalized. But just by tinkering with putting a sign in one place or a number in another place, you can affect the drawing, all right? As a kid, I really didn't appreciate this too much. It's only when I got to high school that I really got it. Just I'm like, oh, I can draw pictures? That's kind of neat, right? It's the basis of, CAD, really. Right? Anyhow, let's do some stuff here. Actually, let me show you what I made. Nix this for a moment. Those little tabs. And this is from the, no, that's mine. This is from your textbook, which is a nice resource, really. But there are some typos here, so I made my own to give you the same information, and hopefully it's better. Let me see if I can get this in the frame so that it is legible. No, it's just a little bit outside. Okay, that's it. Let me explain this. All right. Let's say that you had maybe two transformations happening at the same time, right? Let's just say hypothetically that you have nothing but vertical combinations going on, all right? The order of operations, right, for dealing with this, if you were doing it by hand rather than, say, using your calculator, which largely you will, this is what is suggested, right? If you have vertical combinations, what you might have is maybe a number up in the front here, right? Maybe a number behind whatever the function is, right? Do the vertical stretching first, right, from known y coordinates. This is why I was saying it's good to know, some points. -1, 1, -1, -1, 0, 0, +1, +1. Just know a couple of them for each of the basic toolkit functions, right? Why? Because if you're going to do this by hand, right, or you're trying to make an educated guess as to how a picture will end up looking, all right, vertical stretching would be taking your y value, so something that you would start with, unique to a function, and then multiplying by whatever number is here, right? So if this was the number 2, right, and you took that number 2 and multiplied by the y coordinates, right, of a couple of points, you can expect where the new coordinates would be, right? You're generating them, right? Similarly, all right, if you have the second effect, all right, do the vertical shifting first. So in terms of the actual arithmetic involved, you would multiply your y values first, and then you would add or subtract potentially, depending upon the number that's sitting here. All right, whatever product you got, right? Do that as an afterthought, right? We'll do a couple of these, right? Let's say that you had just horizontal combinations. Now, this is a little bit more of a nuisance because they're inside the function, all right? So there'd be a number potentially here and a number potentially here. There is, again, bear in mind, a counterintuitive sign here, right? If you have this situation, right? Some function gets given to you, right? Where there is no number really written here, right? You assume that that is 1, right? And in that case, all right, it's really not going to have much of an effect, all right? But here's what is suggested to do, all right? Horizontally shift first from the known x coordinates, so you take a couple that you happen to know, all right? -1, -1, 0, +1, the x's specifically. And you, in this case, if you see a minus here, you add whatever that number is there, all right? Then if there is, it would be kind of superfluous, but to perform a horizontal stretch secondly, all right? What that means is you're gonna multiply whatever sum that you have, all right, times, weirdly, the reciprocal of the number that's here. So in the case of, realistically, if there's a 1 here, sitting in the B position, what's 1 over 1? It's just 1. So it's multiplying by 1, so it's kind of unnecessary, all right? But that would be the order of operations. Shift first, technically multiply second, all right? That outcome, having done two things in succession like that, all right, is where you would then park your new dot, all right, that location, in terms of an x value in here, all right? More likely what will happen is what you see underneath this. I'll scroll up now, downward. The situation where you have something that isn't 1, right? When you have something more interesting than the number 1 sitting up in the front, right? It is probably to our advantage, and this is definitely true when we get to the end of the semester, when you're dealing with sinusoidal functions, all right, and sinusoidal transformations, all right, factor something, all right? So, factor first, all right? Given something that is, when you have a b not equal to just a nice 1, all right? Factor, all right? All right? Because it is often easier to horizontally stretch before horizontally shift, all right? We can work around by potentially factoring, all right? Now, what does that mean, all right? Once you have something in the factored form, all right, we'll do the stretching first, all right? Similar to what we would do if we were dealing with vertical things exclusively, all right? What does that mean? It means taking your x values that you happen to know from a regular version of your function, all right? And then multiplying, I just wrote the word times here, the reciprocal basically of whatever the b value is. That's a little tricky. We'll give you an example momentarily to see the point, but that's basically it in a nutshell. You take your x values and then you multiply by 1 over whatever b happens to be at this point, all right? You figure out what b is only after it's factored, okay? Then, all right, from there, you're going to horizontally shift second in the order of operations. And what does that mean? It means once you have this product, whatever it is, you're going to then add whatever this number is. Again, it's counterintuitive to sign, so minus this will be plus that instead. All right? All right? It's whatever number ends up here as a result of factoring, all right, that you're going to add or subtract potentially. All right? Once you have done those two operations in succession in that particular order, that is where you put your new x dot, all right? Now you might be wondering, well, what if you have a combination of horizontal and vertical effects, all right? The good news is they're independent of one another, so you can do them in whatever order you want. In other words, you do your x's first, figure out what that value is, and then figure out what your vertical, your y values are as an afterthought. Right, or vice versa. I would just do the x's first, right? So it doesn't matter if you perform either type of combo first, all right? This is, I would argue, the trickiest thing, all right, if you had to factor something, say, first. So let's do a couple of examples. I may have to open up a blank thing here, so I have a nice white background, or turn the lights on. Let me see if I can get away with turning the lights on. The board itself is white. Yeah, I don't want to turn off my projector because it's kind of finicky. So we'll do this. Let's say that we are given this, and we're going to sketch a graph. Given the function of x is equal to the absolute value of x, so that B shape. Right? Again, when you're tasked with sketching a transformation, they might write it in a goofy sort of a way. Right? If they write it in function notation, remember, you could always change it to just simply y equals the thing. Right? Maybe just for the level of comfort that comes with that. Right? But to distinguish the thing as it was to begin with from the thing that it is becoming, the thing that it is transformed to, in function notation, very often what they do is simply just go for the next letter in the English alphabet. So F for function, and then what follows that, G. All right, so the transformation version of this. Sketch the transformation. Okay, with these changes. F of x plus 1 minus 3. All right. I'm going to use a little subscripts because I happen to like that. All right. And I'll adapt this in a moment. A couple of things. Assuming that everyone is a novice at this point with transformations, you're still getting your feet wet. All right. Use. All right. I hope that it's helpful. Use this as a map. All right. These are the effects. This is where those effects would be situated in the unique function that you have. In this case, the unique function is an absolute value. Again, know a couple of points that make that particular type of graph. All right. So have this on hand. All right. These are what those basic types of parent toolkit functions would look like. We know that this is a V-shaped thing. All right. So therefore, negative 1, 1, 0, 0, and positive 1, 1 would be good to know. Right? Right? You can use your calculator. Again, no sin in that. That's a skill. But if you really want to get a feel for it, do it by hand a couple of times. All right. Anyhow, let's see what actually is happening here. All right. If you read the funky notation, right? This, as you see here, is function notation. The style of writing that is functions, right? Generalizing, right? And this is the actual function itself, right? What you see is that there's something inside here, and there is at the same time something outside here. So we have a combination of a vertical effect and a horizontal effect. Vertical effects are always outside the parentheses, so they're outside the function in question. Horizontal effects are always inside the parentheses, so they're inside the function. This one is not too bad. Here's the model just to sort of point at it too. I'm going to put it over here in green. This is the model of transformation, just not to change my slide. Plus or minus A, technically plus or minus B, X minus H. Some degree would technically be here plus K. This is the whole kit and caboodle. You're not going to get all of those things at the same time realistically, and if you would, you'd use your calculator. But let's compare this to this, and that will make us zero in on, well, which effects are actually occurring. Right? As you can see, there's something sitting in the H position. All right, so therefore we have a horizontal shift, it seems. All right, and simultaneously, there's something outside here that's in the K position. So we have also a vertical shift. Not too complicated. Right? Just remember, the horizontal shifts are counterintuitive, the signs. Right? The vertical shifts are thankfully intuitive, they're fine. Right? But these are the things that we're going to expect to have some effect on this drawing. Right? If regular ordinary function is an absolute value, we would have a picture that looks something like this. Right? And again, it might be good to know these points. 0, 0, 1, 1, in case of a V shape, negative 1, positive 1. Okay? It's probably easiest if you're just manipulating this to pay attention to the vertex here, right, the corner of the V, because it's 0, 0. Those numbers are remarkably easy to deal with, right? But we could affect all of them. All right. If I were going to complete this thought, which I dropped, let me do that now. Here's again the generalized function notation way of writing it. Here is writing it more in tune with the actual function of absolute value here. it would look something like this in the actual actual function, guts. Right? So, all right, if you want to do some arithmetic, all right, we could deal with the vertical stuff first, but let's not bother. All right, of the two options for horizontal transformation effects, close all tabs, please. Take a look at this real quick. I'm gonna have to turn the light off and on. What you see in this case is something that is closer to this situation where the coefficient of x is not written, so you assume it is 1, right? Just a positive 1. So in theory, you're just going to really horizontally shift, is what it is, right? If you were going to just put, multiply after the fact, it would be 1 over 1, which isn't changing anything. Anyhow, here is the minutia, as it would appear with all of these. Right. Start with 0, 0. Right. Kind of trying to confine myself to be in the frame and not in a reflection, unfortunately, with the lights here. If you were to take this coordinate, 0, 0, right, and just zero in on the x value, that's the x, right? Shifting, right, would be taking this value 0 and then performing addition or subtraction depending upon what it actually is. Now remember, it's positive 1, so it's counterintuitive. So you technically would subtract 1 to figure out what the actual value is. Right? So that means that this is going to be x is negative 1 instead. It goes from 0 to ultimately negative 1. Right? At the same time, one needs the y value. Right? The y value would have to be this number 0 here, intuitively just subtracting minus 3. We're shifting. So minus 3, and now you have this. It's like 3D here. You'd have a dot that basically moved, transformed, vertically and horizontally shifted from 0, 0 to this location instead, negative 1, negative 3. Okay. Which, if I'm just going to do it on my little makeshift drawing here, right, you assume that that's negative 1. You'd have a dot basically here. That's now the vertex. A dot, specifically. Okay. If you did, let's just say the other two, for argument's sake. This one, since we've done that. I don't want to get too messy, so I don't have a lot of board space, but let's say that you were analyzing this particular dot in the original drawing here, where it will go to as a result of this transformation. Right? We'll start with the x value. Right? And take into consideration that this is a negative 1 here. In the actual example, it is plus 1 inside the function, so it's counterintuitive because it's a horizontal effect. The signs are counterintuitive, so you're going to, instead of adding 1, you're going to subtract 1. Right? Which means that this actual number is going to be negative 2 instead. Then if you're simultaneously dealing with the y value, you have this. This y value happens to be positive 1, and then we're going to intuitively subtract 3, which means that this is a negative 2. Right, so you're going to put this particular dot now at the location of negative 2, negative 2. So let's see. Negative 2 would be here, down 2 would be there. Right? You could probably guess without doing too much work what's going to happen with this number that is also relevant, right? All right, probably going to be over here, all right? But here's the minutia, here's the details. All right, so if we're going to start with 1, 1, and again, we're dealing with the x's and the y's respectively. And we deal with this x of 1 minus 1 because it's counterintuitive, right? Then the x value is going to be 0, the way the arithmetic works out. And this one, which is a y, minus 3, intuitively, is going to be a negative 2. So this particular dot that is here now goes to this location, 0, negative 2. And you have that. It's the same V shape, it's just horizontally shifted and simultaneously vertically shifted. So those two transformations. Again, there's no sin in using a calculator, right? I'll just put it here for argument's sake. It's always good to use your calculator to verify. That's what I would primarily recommend that you do. So you see x here. And then I'm gonna put this here, sorry. X plus 1 minus 3. All right. Here are the two things that we have. All right. X plus 1 minus 3. I'm sorry for the superimposed gobbledygook, but it's a little bit clearer on the screen here. All right. Here's the graph of the original one, and here's the graph of where we have it. Now, if you want to confirm that those dots that I generated, this one or yourself, this one and this one, where they are in the picture, all right, if you're, in other words, to verify your educated guess, all right, hit trace, and then you may have to move your cursor down to the bottom function first, right? You could see already, just jumping, that it's the coordinates of 0, negative 2, as expected. If you want to verify that the vertex is exactly what we think it is, it's going to be negative 1, negative 3, enter negative 1 here, and if our arithmetic is correct, you'll see that it spits out negative 3. And there you have it. All right, kind of neat, right? Let me show you the more complicated type of problem, and then we'll sort of shift gears here. Let's do basically the same thing, but the type that you have to do a little extra work. I like the absolute value function because it's pretty plain. V shape, it's not even curved, right? Let's say hypothetically that we had this version of a transformation. We were given y equals, I'm going to skip straight to the gist of it here, 2x plus 1 minus 3. And we're going to sketch the transformation. Couple of things. sketch the transformation. We already know that this is a V shape, right? Because it's another one of those absolute values. So if you want, all right, do yourself a favor and maybe just draw it slightly, a little simple picture of what it would be. And as I mentioned, know some points. -1, 1, 0, 0, 1, comma. Okay. This incorporates the same horizontal and vertical shifting, but don't jump the gun, all right? There's an actual B value here that is larger than 1. So what we would do in a situation like this, and I'll just turn my board, pardon me, light off again just to emphasize, what we're going to want to do in a situation like this is, since we're not given something that this is just a 1 here, we're going to factor. That'll make our lives easier. It's more or less this situation. It's not given to us factored, we have to get it to a factor form. Pay attention to basically just the guts of the things that are in parentheses. You can ignore the outside of them almost entirely. Okay. All right. I'm going to start by factoring. If you're going to factor this stuff, just the guts here, 2x plus 1, all right? Remember that when you factor, there's something that's going to be outside of a parentheses when you factor, and some leftovers inside the parentheses. The thing on the outside, ideally, is the greatest common factor. This is going to be a little bit tricky because of the size of the numbers, but it's not impossible, right? They don't immediately have nice factors, other than, like, the greatest common factor technically is 1, right? So in this case, what we're going to do is we're going to borrow that model from earlier, right? Which is we're going to have a B value here. And then we're going to have something ultimately that's divided by B, right, to make it work, right? So if your B value is a 2, all right, I'm going to stick with that, all right? Then reason through, talk yourself through it. 2 times what would be 2x? It would have to be x, of course, if you were going backwards, foiling, you know, or doing the distributing, I should say. Then when you get over to this thing, all right, you want the arithmetic to work out so that if you did distribute 2 to the number that's sitting here, you would end up with the original number. So what is it going to be? It's going to be h with a 2 under it, right? So it's going to be plus 1 with a 2 under it, right? It's this model, HB, right? Let's just verify. 2 times x is 2x. 2 times a half, the 2's would cancel. You'd be left with 1. It's legal. Right. Anyhow, it is in this factored form that you want to proceed with the instructions that are the that horizontal combo. Right. So we're going to horizontally stretch first, which means that we're going to multiply by 1 over the reciprocal of b. All right. All right. And then once we have that product, we're going to then add or subtract depending upon what the signs actually turn out to be. So turn the light off. That means that if we took the numbers, I'll leave the light off for right now. Start with this one, -1, 1. I'm going to leave this blank for right now because we're not considering the vertical, the y value yet. It's not really relevant, right? We're going to take the x value from here, -1, and we're going to multiply by the reciprocal of b. So if the b value is 2, all right, then we're multiplying by a half, basically. What's negative 1 times a half? It's negative 1/2. But don't jump the gun, because we technically have to do the other thing now, which is the horizontal shift. So we have this product. Now we're going to horizontally shift by basically adding or subtracting, depending upon the signs, the number that is the factored version of h. So, all right, we're taking this, negative 1/2, and it just coincidentally is the same number of 1/2, right? Now remember, this is the nuisance, right? Counterintuitive signs. So if it is a positive written here, what we're going to be doing is taking this and subtracting a half. It's annoying, right? Anyhow, this is the minutia, all right? Now we're going to finally get an x value, all right? What is a half minus a half ultimately, right? If, remember the sign combinations from arithmetic, integer stuff, right? When they're the same, they amplify. You actually do addition to arrive at the digit, but it will just be a bigger negative. It takes the sign of the larger magnitude. In this case, it's irrelevant. You could verify with your calculator. Negative a half minus a half is going to be negative 1, right? So this is what you're going to end up with. Negative 1 for the x value. Now, to get an actual dot, we would need the other half of this, namely the y value. All right? So, if you remember, I'm borrowing from this particular dot's numbers here. So this thing that I neglected to this point is really a positive 1. It's this 1 that's here. All right? When you're dealing with the vertical transformation component here, all right, that is thankfully easier. All right? So it's just taking this thing, positive 1, right, from the original dot here, all right, and then intuitively subtracting 3, all right, which means that it's 1 minus 3, which means one of each sign you actually subtract. What do you end up with? You end up with a minus 2. That's your first dot. All right, the hard part, I would argue, not to corrupt your opinion, but the hard part I would say is you got to factor comfortably, and then you have to do this arithmetic in 2 pieces, all right, before you arrive at an actual x. Right? So we're going to have a dot basically at negative 1, negative 2. This particular dot would be transformed to move over to negative 1, negative 2, right? So down 2, all right? Is that right? I believe so. Yeah. So we'll confirm with the calculator as an afterthought. Right? We have negative 1, negative 2. All right, now, you'd have to basically go through the same motions again with the next dot. It's a little tedious, but let's say we were doing this one. All right, we'll arrive at where this is moving to. All right. So 0, 0. The arithmetic will be a lot easier naturally because we're using zeros. Right? But we're going to do the same thing. We're going to take the thing that is the x value here, it's 0, right? And then we're going to multiply by the reciprocal of b, which is a half, right? 1/2. And then what is that going to produce? 0 times anything is actually 0 itself. All right? All right. Now we're going to horizontally shift because it's in the factored form, it's plus 1/2. All right? We're going to add a half to this, or rather subtract a half from this. Which means that for the x component, it's going to be 0 minus a half is just 1/2. Okay? Now to go from what the y was to what the y will be. Let's see. It's just this one vertical component here. All right, so 0, let's see, minus 3 is minus 3 for the y component. Okay, so we have negative a half, negative 3, right? So from here, negative 1/2, and then down 3, 1, 2, 3, you might have a dot like that. All right. I'm going to squeeze in the other one over here, unfortunately. And then we'll sort of change the subject. Let's see. Last one of these, 0, 1, 1. Pardon me, 1, 1. This is a positive 1 in this case. Right. We're taking that 1 and then multiplying it by a half, right, and then producing the product of positive 1/2, right, and then subtracting the factored version of h here. So it's going to be 1/2 minus a half. Right. Sorry, I'm kind of squeezing that in there. Which means if it's positive a half minus a half, they cancel. Right? Which means, for lack of better space here, they're going to land the x value at 0. If we do the y components now, again, it's nicely intuitive. It's going to be this number of positive 1 minus 3, which means that it should just be negative 2. Okay. So this dot that was here should be 0 and then down 2, 1, 2. So you see a V that's kind of narrowed, right? Like that. All right. Let's verify with our calculator. So I'm going to use the light of my screen here to help me see, and I'll delete this stuff. Okay. All right, math, no, quit. Okay. X. Here's original V-shaped function, absolute value, right? And then underneath it, I have to replicate that, so I'm going to put the same absolute, no, don't do that. Same absolute value, x, but I'm going to put in the original one. I don't have to tinker with it, so I'm just going to put 2x plus 1 on the inside of the modulus lines. So 2x minus 1, pardon me, plus 1. And then put minus 3, park that on the outside, so minus 3. If you get an error message, it could just be that you've accidentally put the wrong button here. This negative that's down here is only for coefficients. Right, so if you have to separate terms, just use regular subtraction. Right. That's the only thing I could foresee as being an issue. Now I'm going to graph this. Here's the original V shape, right? And here's what the transformation should look like. Right? If the arithmetic is correct, all right, and I would always verify with a calculator, all right? Let's see if we get these points as predicted, all right? So what we would do is we're going to scroll, well, hit trace first to get the cursor, and we're going to scroll down to the other one, and you could see 0, negative 2 is where this point is, all right? As predicted, check the other two, all right? We'll put in negative 1, and see that we get negative 2 is that. All right, so I'm going to put negative 1, and we get, thankfully, negative 2. Cool. All right, and try that one. All right, negative 1/2. So just for the sake of simplicity, I'm going to put negative 0.5. All right, so negative 0.5. All right, enter. And you see you get -3, right? Neat, right? -1/2, -3. All right. Kind of cool, right? All right. All right, I'm beating a dead horse now. Let's sort of shift gears now. Don't go to sleep. Let me put the light back on, 'cause I can't see. All right, I'm gonna do a little theory stuff first, and then some algebra, and then I'll stop soon. There's this drawing that I came up with to summarize. Let's see, features of a graph. You're gonna see basically this same picture a couple of times from now until the end of the semester, because I wanted it to slowly evolve into something of greater complexity. Right now, we don't want to overcomplicate things unnecessarily. Get this out of the way. Okay, make sure that this is in the frame. It's always kind of a pain in the neck. Don't get killed now. See Flat Stanley, that was a children's book. I often think of that. I love that story. I don't want to be Flat Stanley though. Anyhow, I'm gonna have to shrink this and we get it. Are we in the frame? Let's have to check. I believe that's in the frame. Good. All right, now, as I said, this is a sort of the first version of an evolving features of a graph summary, right? The stuff that we are aware of at this point in the conversation of functions, right? Graph features of functions, right? We're going to start with, what do we know? We know the basic toolkit functions, meaning we know what the pictures look like from our basic toolkit parent functions, and that they're basically controlled by changing the degree. So depending upon the degree, that will establish what the shape is, all right? Then there are these technical terms here to summarize. There's behavior, all right? There's end behavior, which has to do with the arrows, and then there's something called local behavior, which happens to do with interesting points that are in between, you know? There are famously intercepts that are x and y intercepts. I think if you had any experience with graphing, straight lines and stuff, you probably heard of x and y intercepts. Y-intercepts are the point where the curve or the line crosses the y-axis. X-intercepts are where the curve or the line crosses the x-axis. Right? Then there are these other types of local points known as turning points. They're sometimes called extrema or relative extrema. Right? You can think of them as being the low point, a minimum, right? Or a high point, a maximum. Minima is the plural of minimum, right? Maxima is not just a Nissan, right? It's the high point of, it's a plural of high point, maximum, right? Think of them as being peaks and valleys in the picture. What's going to be more important to us right now is this stuff over here. So kind of zero in on this for a moment, right? I do have to be a little bit better than as I've described it here, right? If you have something that's known as an even function, all right? Say, for example, y equals x squared, right? The parabola shape, right? Which looks like this, right? If you know that you have an even function, all right, you can make a prediction about how the picture looks, right, in terms of its end behavior, in terms of its arrows. I sort of jumped the gun a little bit. I said, and this isn't, it's true, but I should be more specific. Even functions have arrows up. What I want you to do, if you're following along, to annotate one little thing. I should say arrows both up or both down. All right? In other words, like this together or like this together. It really depends on whether there's a sign up in the front. You know, vertical reflection is controlled by a negative up in the front. Anyhow, when you have odd functions, as in the case of y equals x cubed, right? Then you have a graph that looks like this, right? More or less one of each, right? So make this distinction. Even functions, same direction, both up, same, or one of each. That is one up, one down, right? Like that, right? Now, that's sort of a graphical way of interpreting this, right? Even functions are the end behavior, the arrows will both be up or both down. Generally, they start as being up, right? Which is why I say arrows up, right? But if you have an odd, it's one of each, one down, one up, right? There's an algebraic way of proving this, all right? That you have an even function per se or an odd function per se, and these are the models. In other words, if you get a balanced equation by taking whatever you're given, your unique function, and instead opting for a negative input, they should equal, right? If they don't equal, then you go one step further and check to see that it's an odd function, which is where you have the addition of a negative symbol outside in addition to it being inside. Right? It'll give you some example in a moment. Right? But just think about it this way. Right? One of the conditions of the picture, or the features of the picture that we want to kind of keep in mind is the end behavior, meaning the arrows. Right? These two, I've already said, are an example of an even function and an odd function specifically. If I'm going to go and use these models that we have, rules, let's see if that can verify algebraically that status. If something is even, then this would be true. That simply opting for a negative input is going to still give me the same thing. It's going to balance, right? So if I were going to take this for example, we're going to, as an example, decide whether it's even, odd, or neither. All right. Let's try that on this function. X cubed plus 2x. Okay. On one side of this, testing to see if it's even first. All right. We'll see if it balances. All right. I'm going to put these interesting guts here. All right. X cubed plus 2x. And then on the opposite side, hoping that they equal, because that will prove that it's even. All right. I'm going to do the same thing. But I'm going to have to do one little alteration. In place of the x's, I have to have negative values. So what I'm going to do is I'm going to park little parentheses and a negative here and here. And see if I get identical features on opposite sides of this equal sign. All right. For right now, I'm stuck with these two terms. There's nothing I could really do with them, so I'm just going to leave them there. But for this, I'm going to try to straighten it out, right? The x is not going to change. It's still going to be x cubed, right? But this 3 will also affect the coefficient that is technically a -1, right? If we think about the minutia, the actual arithmetic involved here of -1 cubed, that would be -1 times -1 times -1. And ultimately, what would you be left with? You'd be left with a negative up in the front. Because a negative times a negative may be a positive, but a positive times the remaining -1 is going to return it to negative status. So leave that alone for right now, right? Same thing over here. What are you going to do if you straighten this out? This is essentially 2 times -1, which means that it's going to be minus 2x up in the front, right? Now, if you want, you could stick in some simple numbers, all right, just to verify here, right? Let's just say, because you can tell right away these are not equal, right? These are both positive and these are both negative, so you can just call it quits right now. But if you want to be more satisfied, just throw in a number, as long as it's the same number consistently. Let's say that you throw in the number 1, because 1 is really super easy to use. Put a 1 here and a 1 here, and see what we get. 1 cubed is 1. 2 times 1 is plus 2. 1 plus 2 is 3. Let's see what that equals over here. 1 cubed would just be the 1 again. 1 with attached negative is minus 1. Right? And then 1 times -2 would be minus 2. And in this case, you'd get -3. Now, in spite of their similarity, what would you say is the case here? Are these things genuinely equal to one another or not? They're not. This is a +3 and this is a -3. These are not equal, all right? Therefore, this is not an even function, right? They don't balance. If there's no balance, you can't say that. Now, that doesn't mean it's not odd, perhaps, or maybe neither of them, but we're going to check by doing a little extra work here. Right? Okay. You can save yourself a little bit of trouble, right? What I'll do is, just for the sake of space, I'll get rid of this. And these. If something is odd, then this is the situation. The function would be equal if there is this extra negative outside of it. Right? So, with that extra feature, input and output, I'm going to take what I had here, all right, to spare myself a little bit of trouble, and replicate it. Right? I got it to be x cubed plus 2x on one side. If we're following this sort of rule here, all right, then it's almost the same thing. It would be -x cubed minus 2x, but in addition, outside of that, there would happen to be this extra negative here, all right, if this is in fact odd, all right? Now again, that may not be too comfortable. You could, if you wanted to, distribute this and you'll see what the effect is, all right? But if you want maybe a little bit more satisfaction, there's no sin in putting a number here and here and here, right? And then going through the minutia, all right? We already know that if we put a 1 in here and here, that we're going to get 3 ultimately, as we had before. If we had, from straightening this out earlier, I'll get out of the way, that this by itself is -3. What's -3 with an extra negative here? Right? It would ultimately be negative times negative, which means that you'd end up with a +3 as you do here. And in this case, it would in fact check out, right? This thing, x cubed plus 2x, the original function, is an odd function, apparently. Okay. That's a way of proving it. If after doing all of this you end up with something that's still doesn't balance, all right? And that means it is neither. There's one more sheet here, and then I'll stop. Okay. There are, just to kind of keep in your head, some things to consider. These scenarios. I made another one of these blank sheets. This has to do with the discussion of symmetry. Right? I made this to summarize, so I'll give you some examples to annotate. That is, scribble them on the sheet just for reference. And I'll get this out of the way. I gotta make sure it's in the frame. That's available for me to do. Okay, so this is gonna get shrunk. Let me give it that X. Shrinky dink here. Get a little bit larger. Okay. This should be just inside the frame. Oh, come on. Sometimes Microsoft really sucks. They're going to fight with me when I'm doing something important. Okay. That looks like it's just inside. Okay. Now, to give you an idea of what symmetry is, all right, basically, symmetry is when a picture looks the same before and after, in the context of transformations, before and after. All right, so when the drawings look unchanged, even if they've been reflected somehow. Now, you can have a horizontal symmetry exhibited, all right, or vertical symmetry exhibited, all right, both simultaneously, right, neither, or both consecutively. This is odd, basically, over here. This pertains to what we were just talking about, the situation when we had odd functions. Odd functions exhibit symmetry after you horizontally reflect and then vertically reflect. Okay? Horizontal symmetry is more or less the even situation. So even functions have horizontal symmetry. I want to get rid of that thing in the corner because it's annoying me. I'm not even sure why this is here. Yeah, okay. Come on. Well, that's a nuisance. I wish I could move it. Whatever. Alright, just to reiterate, I'm sorry, I'm just getting distracted with the stupid computer here. Even functions exhibit this type of symmetry. Horizontal symmetry means when you have symmetry about the y-axis, when something is reflected about the y-axis, is horizontally reflected. Horizontal reflection. Odd functions, right? These are when you're reflecting in consecutive order. All right? When something looks the same after you do two steps. All right? They call that symmetry about the origin. All right? To summarize that, it means horizontally reflected and then also vertically reflected. That is to have symmetry about the origin or both consecutively, to call something an odd function. Right? Now, as an example to illustrate that this is true, right, here is y equals x squared, which we already know makes the parabola shape. Right. If one were to take the parabola shape and reflect it horizontally, all right, that's like this. All right, that is about the y-axis, which is what I'm dashing here. All right, you were to spin something this way, backwards and forwards, it would be indistinguishable before and after the reflection, or before and after the transformation, if you prefer to say it that way. Right? That's an example of an even function, exhibits horizontal symmetry or symmetry about the y-axis, horizontally reflected. It's all the same difference. Right? The thing that would be, like the example we just had, that is both of these consecutively, otherwise known as odd functions, would be this. Y equals x cubed, right, is the picture associated, right? You know it's the stained alive pose, right? Well, in order for the picture to look before and after the same, all right, that is to say, to look the same before and after, right, something has occurred, some transformations have occurred in sequence, right? Here's what you would do. I'm going to do it in two different colors. If you took the original thing and then you horizontally reflected it, all right, this is what you'd end up with to start with. Looks like DNA now. What is in red? All right. If you then took the red curve and then vertically reflected it, what you would end up with is that this point would be down here and this point would be up here, and you'd be where you were to begin with, in green here. All right. That is a sequence of transformation. That is to say, it's those things, those effects, transformations consecutively, horizontally reflected and then also vertically reflected. To summarize it is often just simply stated symmetry about the origin. Right. There are other cases though, vertical only, neither, or something technically simultaneous. Let me give you each one of those. All right. Let's start with neither. An example of something that has neither horizontal nor vertical symmetry would be the cube root, I believe. No, I'm sorry. 2 to the x. All right. So an exponential function, which is like chapter 6 stuff. Basically, a function that looks like this, where the variable is the actual exponent. Right? It would look like this as a picture. I'm going to put it in green, just not to confuse it with that. You'd have a curve that looks like this. Right? Imagine that you horizontally reflected it. This point would then be this way, shifting downward, a decay, that you'd say. If you were then vertically reflecting it afterward, hoping that it would be an odd type of function, all right, you'd have something down here instead. All right? It's never going to look the same even if you employ both tricks in sequence. So this is an example of something that has neither type of symmetry, all right? 2 to the x, where the x is the degree. There is something technically that is both simultaneously, though, and this one's kind of funny. Y equals 0, known as the x-axis, technically. All right, is the picture of y equals 0. Y equals 0 is the x-axis. I'm going to emphasize it in red here, just to sort of superimpose upon it. All right. Imagine, although it would be pretty silly, right? Imagine you horizontally reflected this. It would look like the same thing. All right. Imagine that you vertically reflected this. There's really no way to go. All right. It is both of those conditions simultaneously. Right. It's not going to change. Right. There is technically another one, but you got to be careful because it's not really a function anymore. All right, if you mess with it. To illustrate something that technically has vertical symmetry, it's this hypothetical situation of y equals the square root of x. Now, if you remember from the parent toolkit function handout, with this awful square here, all right, the square root function only looks like half of a parabola sideways, all right? It looks like this, right? That curve, right? That is for a technicality, right? The definition of a function, the easiest way to remember it is that there are no repeat x values, but hypothetically, were a person to take into consideration not just the principal square root, which is the positive basically, but also technically the negative, you would have repeat x values because you'd have two different y's with the same x. You'd have the other half of this parabola, that's sort of a sideways parabola, all right? And that would be not a function by definition, right? Right. So your calculator, were you to enter basically y equals the square root, is never going to draw the bottom of this because then it's not a function, right? But for the sake of the conversation discussing vertical symmetry, this is something that if you were to preserve both the positive and negative outcomes here, you would have something that looks like this, right? Therefore, it would have vertical symmetry, whether you were to rotate it like that. It would look the same before and after the effect has occurred, right? Anyhow, that's basically it, right? It's kind of interesting, I think. Right? Let me leave it at that. We are now at an hour 50. I think that's more than adequate stuff, right? Hopefully, the air conditioner cooperated today, so I don't think it was even blowing, right? So you probably heard me, okay? All right, I'll see you guys on Thursday, all right? Be careful out there. Do your homework, please.